All right, guys. Today I'm talking about scientific notation. This is going to be pretty short. This is probably something you've already dealt with, talked about in your math classes. I'm just going to make short work of this. Here we go. So scientific notation is just a way to show very large and very small numbers, the kind we have to deal with in chemistry, in a more compact and easier to deal with way. Because the problem is when you're trying to write out numbers like this and this, it's very likely that you'll forget the zeros. You'll forget and miss zeros, add too many, add not enough. We're good at handling like three zeros. We're not good at, our brain isn't good at like making sure I've got 14 and not 15 zeros. Like it's just kind of difficult to deal with. So a method called scientific notation. Scientific notation makes it much easier to deal with them. So fundamentally, scientific notation expresses things as a times x, 10 to the n. So a is a number that is between 1 and 10, not including 10. The net upshot is it's got some non-zero digit in front of a decimal point, and it may or may not have anything afterwards. So if it's only got one significant figure, it might be 2, but it could be like 2.46. But numbers like 0.13 are not going to be numbers you see in scientific notation, nor are you going to see things like 143 times 10 to the something. That's not scientific notation either. It's only one non-zero digit to the left of the decimal point, and then times some 10 to some power, some whole number. It could be positive or negative, but it's going to be a whole number. So here's how we do all this. Here's an example. So proper scientific notation, only one number to the left of the decimal point times some whole number. Here, I'm taking this number, this becomes this, this becomes this. So again, these all follow the same rule. One number to the left of the decimal point. This is a positive exponent, negative exponent, but they're both whole numbers. So here's how it works. Actually, there's all this, my slides go through all this extra stuff. Here's fundamentally, I think, the thing to remember about scientific notation, is that 100 is 10 to the 2. 1,000 is 10 to the 3. Right? So fundamentally, when we have this part of the scientific notation that's to the right that is times 10 to something, it's times 100, 1,000, a million, something like that. So here's how fundamentally I think the best way to think about this working is. Say I've got a number like, let's do a nice simple one like 2,800, right? And I want to put this in scientific notation. Well, the point of scientific notation is I want to still represent the same value, but I want to show it a different way. So what I'm going to do is I'm going to take this decimal point, I'm going to move it to the left just 1. I'm going to move it more in a minute, but for the moment, I'm just going to move it to the left 1. Now, there's a couple things I want to make sure I discuss. So one, I've changed the value, right? What have I done? I've effectively divided it by 10. In order to restore the same value, because this is now 280, this doesn't make any sense. This is not 2,800. I have to multiply it by 10. So, easy. Right? Now I'm going to move the decimal point one more time. I'm going to move it again, so I get 28. Well, I've divided by 10 again. Well, now I've got to go 10 times 10. Well, okay, that's great, but there's an easier way to write 10 times 10. 10 squared, right? And if I move it a final time, 2.8 times 10 to the third. Now, what I think helps is to think of this original number, 2,800, as having a times 10 to the 0 out here. Does anyone, hopefully you remember what anything to the 0 equals? That equals 1, right? So this is just 2,800, but there's sort of when we have decimal notation, we have an imaginary 10 to the 0 out there. Fundamentally, scientific notation works this way. Every time you move the decimal point to the left, so every time you move it to the left, the exponent increases by 1. Every time you move it to the right, the exponent decreases by 1. So if I have 0.000496, if I move the decimal point 1, 2, 3, 4, I get 4.96 times 10 to the negative 4 because I moved it 4 times to the right. So I always move the decimal point to park it right behind the first non-zero digit. If I stopped early, so let's say, for example, I've got 0.00112. If I only move it 2 spaces, 0.112 times 10 to the negative 2, that is not proper scientific notation. The decimal needs to be parked behind the first non-zero digit to be proper scientific notation. Another cool thing about scientific notation is that if you if I had, let's go back to 2800, right, and I move the decimal point 1, 2, 3, remember, so at the beginning, I didn't write a decimal point. So are these zeros significant or not significant? They're not significant. So when we go to 2.8 times 10 to the third, there's no reason to write them. The whole point of putting the decimal point where we do ensures that only significant figures are written in the exponent, or not the exponent, sorry, in the coefficient. This is the exponent. In the coefficient, we only have significant figures represented. So you never have to guess. When you see a number that's in proper scientific notation, it's got the number of significant figures is right there laid bare before you, right? So, actually, let's do these. Go ahead and pause it and try this. So the first one becomes 2.1 times 10 to the 7th. The next one becomes 3.402 times 10 to the negative 5th. This one's 4.05 times 10 to the 2nd. Now this last one's kind of funny. You might think, well, what's the problem here? This is not proper scientific notation. Even though it's already got a 10 to the 3, this is not what makes something scientific notation. It's got to have this and the decimal immediately behind the first non-zero digit. So what I'm going to do is I'm going to move the decimal 1 to the left, which increases the exponent by 1. All right? 9.2 times 10 to the 4th. Now, to put something back in back in decimal notation, you just move the decimal place so that you get back to 10 to the 0. So here and here.